Assalamu alaikum. Everyone can hear me?
Yes.
Yes, good.
Yes,
Okay, so I hope that you have watched the online lecture, at least the first one, which I posted yesterday. So I am now open to answer your questions. If you have any question, you can please ask me any question and I'll try to explain it to you. If you, the quality of the lecture is not perfect, but this is what I can do within the limited resources that we have. So I hope it was clear. And if you have any question, please, now if you go to the participant option, you can basically, there is an option that you can raise your hand. So from there, then I'll see that you have a question and you want to say something, then okay, we have, yeah, so please unmute your mic and start. What's
Assalamu alaikum, ma'am.
Alaikum
So
salam.
basically, the thing is, could you please record your lectures in a landscape mode? Because when we view it in our laptops, it will be on a full screen then.
Yeah, I was trying to make it, I think, portrait, so it's easy to you to see it, but I have both ways. So I also can scan for you the pages where I wrote. Yeah,
Yes,
so
that will be
yeah, I thought that it will be easier for you to see it when they are vertical. I know that the font looks more smaller, but I don't want you to keep bending your neck while you are seeing.
okay. Thank you. Yeah.
Yeah, but I'll try to upload the notes so they can in a PDF form so that you can view them easily. Okay, I also just want to tell you that we are not planning to cover everything that we were planning to cover earlier. So we want to just focus on the main points that we want you to take out from this course. I mean, we are limited but by these circumstances everywhere and the current situation. So we hope that you understand that. And if you face issues, please don't suffer alone. You need to tell us so we know how can we help you. I mean, I don't want anybody to be suffering and they are just not telling us. We want to know if there are any issues, how can we help you, how can we overcome them in the best way. So any of you have a question on the lecture, any general question, anything that you like to discuss? I mean, the form is, I want to hear from you. I mean, we are not seeing each other since long time, but I want to hear from you. So I have Ali Samik, please go ahead. Unmute your mic and start talking.
Assalamu alaikum, ma'am. Can you hear me?
Yes, I can.
Okay, ma'am. As we all know that this is a new time for all of us and a really good initiative in regard to online learning. And just one request, because since we're going to have 2 sessions per week, if it is possible for you to conduct a 15-minute summary before every session. For example, if we start at 2, by 2:15 you give us a summary of the lecture, and then after that we can ask our questions, because we think if you just summarize it for one bit, it will be a bit easier for us, because live learning is, we are mostly aware of live learning, like seeing you talk. On the recorded lecture things, I couldn't I felt that there was still a need of clarification. So if it's possible, if you could summarize the lecture and just note down and tell us what the topics were, and then we can ask questions on them, or we could research more on them, find practice questions, and further more on that, if it's possible.
Yeah, okay. I mean, I am okay with that. I can do that now. I have the same pages which I wrote during the video, so I can give you just quick summary on what I did in the video. And then if you have questions, then might be you remember your questions and you can ask them.
Yes, yes. Thank you so much, ma'am.
Most welcome. Just let me try to share my screen. But the video, I was trying to find the best way. How can I share my screen for the video, but it's not the best way. So let me, okay. Is it visible? Can you see? Ali, can you see? I just want somebody answer on behalf of the rest.
Yes, ma'am, we can see it.
Yes.
Yeah, okay. Okay, so I'll just go over this. Okay, so basically, if you can see here, we are in this chapter talking about the feedback systems. So, and that's a very important topic to cover in the integrated circuit because they have very wide range of application, and almost every system will have, I mean, it's very rare that you use an amplifier in the open loop configuration. So it's important for us to understand and study the behavior or the feedback. So basically, this is a general block diagram of a feedback system. You have the input coming. This is what we call the feed forward system. And then we have the feedback network here. And this X of F, it's a name that we are giving to the output of the feedback. Okay. So now, you want to find the transfer function of this loop, you basically just try to see what is coming here. We have the input is coming with a positive sign, the feedback component with the negative. So we are just subtracting them here. So you have at this point, you have X minus X of F. Okay, and this whole is going to be multiplied with A1. And then you get the output Y. But then if you want to ask yourself, what is this X of F? It's basically our output Y multiplied with the K. Okay, Usman is raising hand. So do you have a question about this part? Then go ahead.
Ma'am, there are visibility issues. Can we please upload PDF of these right now? Because I
Right
couldn't
now,
see
I don't have it right now. It will take me time to take because we also don't have a scanner at home. So I have to take the images, the pictures of them, and then I have to sum them all together and make a single PDF. So I'll do that today. And we will also have another session on Wednesday. So if still you feel that there is something you did not get or it's not clear, I'll try to turn off the slide. It's here might be something shining on it. But then let's see if you will still have questions we can answer.
Okay.
Is it more good or more bad?
No effect, ma'am.
It's fine, or I should turn on the light?
It has very minute effects.
Yeah, okay.
Doesn't change anything.
The light on. Okay. Anybody else has a question on this? I can't see any more hand. Okay, I'll try to upload for you the notes by today so that you can see them. And on Wednesday, any remaining question or you want to ask on the email, no problem. I'll be happy to answer you. Okay, then basically you just do a simple rearrangement here, and then we get what we call it the closed loop transfer function. So if there was just a forward path, there is no this feedback, then we are going to get only this A1. However, if we close the loop, you can see that we are getting A1 divided by 1 plus K times A1. So the gain has been reduced from A1 by a factor of 1 plus K1. This means that the closed loop gain is much smaller than the open loop gain. Okay, let me see who's having a question. One minute. It's not so easy to see in this view. I don't want to close this. Ali, I see Ali is raising his hand. Do you have a question?
Yes, ma'am.
Yes.
Am I clear?
Yes, yes.
Ma'am, are A1 and K1 both constants? What is the importance of these constants?
Yeah, A1 is basically a gain of your amplifier. Means it can
Okay.
be GMR out, it can be any, like whatever is in this. It's not just we are going to have a box here, we will place it by an amplifier. So it has a gain. So it is the gain of that amplifier. Is it GMR out square, whatever the amplifier, it's the gain of that amplifier. Similarly, K, it can be a constant value that's coming through a ratio of resistor that we are going to see. And basically, so it depends on the circuit that it's there. They might not be a constant, but they are depending on the circuit that we have there.
Thank you, ma'am.
Thank you. Anybody else has a question? Okay, seems to be no. Ali, you still have something to say?
No, ma'am.
Okay, then by mistake. Then Uzair, I have Uzair is raising hand.
Yes, ma'am. I just
Yes.
want to say that this is not visible at all. Like I'm trying my best, but I cannot figure it out.
Yeah, I'm also having a very limited resources. I don't know how can I make it more visible. Should raise it up.
Like had it been a little more visible, we could have figured it out with your words, but even the letters are not visible.
Try to make the sheet up. Is this better?
Yes, ma'am, it is better.
Okay. So I'll just go again through it. So this is our block diagram. And we have our X input is coming here. This is X of F. We are at this point subtracting them, multiplying with A1, and then we are reaching to our output Y. Basically, the main to realize that your X of F is just K multiplied with Y. So it's Y multiplied by K, then comes to X of F. And then you do some simple math here, and then you will reach to your Y over X is equal to A1 divided by 1 plus K times A1. The main thing that I want you to understand from here is that your gain in the total overall circuit has been reduced. So initially it was, let's say, GMR out. Now it will be not GMR out, will be GMR out divided by 1 plus K times GMR out. So we have lost in terms of gain by forming the feedback. This is the main concept, let's say, from this page here, that having a gain, feedback has led to losing in terms of gain. So our closed loop gain always will also look as it's the open loop gain divided by 1 plus K times the open loop gain. Now, who else want to ask a question? Sayyid Hamza.
Yes, my Assalamu alaikum.
Alaikum
Back to
assalam.
the configuration, the diagram that you draw.
In the diagram, yes.
Yes, this one. Can you just hold it right there? I just need to
Yes,
draw
okay.
this. And also, can you like zoom in for a bit? थोड़ा सा clear नहीं है बिल्कुल भी.
Like this.
Yeah, this is fine.
Yeah, this means I have to have one books more to make this. Okay, 1 minute. You can't see my setup. It's so funny, like the things.
I think, ma'am, it's probably the light that's shining off the paper.
The
उसकी वजह से
light,
शायद
I
हुआ।
don't know. It's like it's not meant to be a studio or the home. So the lights, they are not so perfect as well for the
Yeah,
video.
this is perfect, ma'am. This is perfect.
Okay. So I mean, now you can see the block diagram. The main thing, again, after you do, I'll share with you the sheets so you can view them. Yeah, I guess somebody else having questions. Let's see, who's that? No, I can't see somebody. 1 minute. No one is having question. Anybody have a question? Please go ahead because I cannot see anybody raising hand. Okay, Mustafa Arshad, you are just raised your hand. So you want to say something?
Yes, ma'am.
Yes.
So basically, I have a question in the loop gain.
Yes.
So basically, the open loop transfer function A1 of S, which you've
Yes.
written down, is
Yes.
basically the Laplace transform of what we've been doing above, the Vn over V test.
Yes.
And yeah, please go ahead.
Yeah, I just want to say that at this moment, I just did not include the S part here. When S, it will be the Laplace transform. If you want to go to the time domain, then you need to do the inverse of the Laplace transform. So the things are, linked with each other, but at this moment, we are not going to be doing that. We just want to focus on it. Just looking at it in the form where we have S. So we know where the location of the poles and the zeros.
Okay, thank you. Yeah.
So again, this is the main thing that I wanted you to get from here, that we are losing in terms of our gain. Okay, Ali, can you please go ahead?
Yes, ma'am.
Yes.
Ma'am, could you highlight the difference between the closed loop gain and the open loop gain in this case scenario?
Yeah, A1 is our, so A1 alone, assume that we don't have this path down. So it just X goes to A1, comes Y. This is the open loop. Okay, if we are closing the loop, then we're taking something from Y and feeding it back to the input. So the open loop gain is A1. The closed loop is what we have gain, is that what we have derived here. Okay?
Thank you, ma'am.
Okay. Now if we're done from the gain, let's see what happens in terms of the bandwidth. And that's a bit, I need little bit of focus. So if we assume that we have an open loop transfer function that is basically A0, which is the DC gain, divided by 1 plus S over what is this? Omega 0, which is the omega 0 is the bandwidth, or the 3 dB bandwidth of our, just want to make sure that we are still recording. Okay, we are still recording. Let's go back to the screen here. Okay, so now I just want to link this to you to a normal amplifier that you know it before. Assume that we have this row here. This is our amplifier, and this is the VN. This is RD, VDD. This is CL, and this is V out. If you remember this amplifier, it's a common source amplifier, and I have a load capacitor. If you remember when we wrote the transfer function of this amplifier. So now we are just calling our input as X and our output as Y. Fix the Y here. Okay, so now this is an open loop amplifier that basically have a transfer function that we are calling it here A1 of S equals to the DC gain, which is GM RD in parallel with the R out, as you remember, divided by 1 plus S over RD in parallel with the R out times CL. So this is the location of the pole. Here we have just a single pole in ours. We are ignoring the internal capacitors of the amplifier. We're just taking care of the CL. So what I wanted you to see, so this is the DC gain. I mean, this is, I just wrote it so quickly. You can write in your own way that you make that, how to say this, make the entire small signal model and find the gain, whatever you want. And this is our omega 0, which is our bandwidth. So you remember when we used to find any pole, it's 1 omega p 1 over c times r, the impedance that it's seeing. Okay. So now this is our omega 0 and this is our DC gain. Now, assuming that the entire blocks of A1 that we were showing in the feedback has this, for just simplicity now, it has this amplifier that is here. Just, I was right saying this so that you can understand now why this A1 of S looks like this. So it's a DC gain divided by 1 plus S over omega 0, and omega 0 is the dominant pole of our amplifier. So now this is just the open loop one. Include in the previous sheet, we were not taking care that there is a bandwidth. We were assuming that it's an infinite bandwidth. Now here we are not, in order to be more accurate, we're not assuming that it's infinite bandwidth, but we are assuming that the bandwidth is limited and it's equal to omega 0. Okay, so now we do furthermore calculations in order to reach to the what is the closed loop transfer function, including this bandwidth information. So we're not assuming the bandwidth infinite anymore. So we get that our gain, now new gain, which is the closed loop gain, is A0 divided by 1 plus KA0 over 1 plus S omega over, omega 0 multiplied with 1 plus K omega 0. So now this is our new bandwidth and this is our new gain. Our gain has been reduced, the DC gain, by a factor of 1 plus K times A0, while this one has been multiplied. So it's not omega 0, it's now omega 0 multiplied by 1 plus K times omega 0. So what do we understand from here? We take two important things. The first, that our gain has been reduced by a factor of 1 plus KA0, while our bandwidth has been extended by the same factor. So this is the figure that I was showing you here. This is a very, very important figure that you will see it over and over. So now this is, as you remember from the body plot that we were drawing. So initially in the open loop case, in the blue line here, the gain is A0 or A1, that it's a DC gain value, and the bandwidth is omega 0. Now, once we close the loop in the red line here, the gain became A0 divided by 1 plus K times A0, while the bandwidth has been extended from omega 0 to omega 0 1 plus K times A0. Okay, so these are the two important points that I want you to know. Then once we close the feedback, we close the loop, we have a feedback system. we are going to lose in our gain, but we will gain a benefit in our bandwidth. So we will lose bandwidth, we will lose gain, but by the same factor, we will gain in terms of bandwidth. Okay, so these are, I mean, you lose on one thing and you gain on the other side to overcome the issues. Okay, so any question on this? This is very, very important to know. Yes, Ali, please go ahead.
Yes, ma'am. The last line you said that
Yes.
for gaining one thing, you have to lose one thing. Could you re-explain on that point? And number two, you
Yes.
said that there is a certain point on which we shift from open loop to closed loop. So could you re-explain on that, the red line?
Here?
Yes.
Okay, now in the first question, I said when we close the loop, by our calculation with all what we have derived from the two sheets, we found that we have lost gain. So once you write your transfer function, initially here, just assuming that we have infinite bandwidth, we were having that our gain has been lost significantly, I mean, by this factor. So it's instead of being A1, it's now the original A1 divided by 1 plus K times A1. So this is losing. I mean, it's not A1 anymore. You are dividing it by another value. So, I mean, 5 is always greater than 5 divided by 3. So
yes.
Yeah, this means that you have lost your bandwidth. So your gain is not 5 anymore. It became, let's say, 1.3 or something. So you have lost in gain. Agreed on that?
Yes.
Okay, now we did the similar derivation, but now we were not considering that A1 is equal to A0. It's now, if you're just assuming it A0, this means you are assuming infinite bandwidth. Okay?
Yes.
But now
yes.
we are assuming that the bandwidth is limited and it's given by this one. You remember that we discussed when we talked about the frequency response of the amplifier, that we have a pole here, and therefore
yes.
it's going to be a flat line. Where is this? It's going to be a flat line, your gain, until you meet the first pole, then you will start to decay by minus 20 dB per decade.
Okay.
You remember that?
Yes.
Yeah, that is from the frequency response when we discussed about how to draw the body plot. Now, this is our blue line. That let's call it. Make sure I don't have this one. This is the open loop case, and the red one is the closed loop. Okay. It's visible. Okay, so now once we close the loop, we are again trying to draw the new body plot, but we are overlaying them on the same plot, so we see the difference between them. Okay, so now what is our new gain, DC gain? It became A0 divided by 1 times 1 plus KA0. So this is our new, and we continue until we meet our new pole, which is located at omega 0 multiplied by 1 plus Ka0. Now, if you want to compare the plot in the red and the one in the blue, you can see that you have much lower gain, but you have much higher gain, much higher bandwidth. So these, I mean, we lost. You can see instead of having A0, you have this gain, but the bandwidth has been extended.
Okay.
Okay?
Yes.
So these are, let's say, the two important points that you must know.
Okay.
Anybody have a question on them? Okay, seems to be they are clear. And again, I'll post the sheets for you so you can look at them carefully. Now, the other, I guess I'm going in, hopefully in order. This is the loop gain concept. It's also important, but it's not difficult. I mean, it's not need much intelligence to understand as the previous ones. So here, basically, it's important to know how much our loop, I mean, the entire, let's say, a circle, this our loop, how much gain it has. Okay, and it's useful in many studying the stability and other concepts of the amplifier. Okay, so the solution or the way to do that, to find the loop gain, is that you need to break the loop at any point you like and make your input as short. Okay, so you need to make your input short, mean applying a zero input, and you need to open the loop somewhere, break it, and apply a v-test at one direction here that goes through the loop. I mean, you cannot assume that, I mean, you need to keep direction of the arrow. You cannot assume that your input will go in the opposite direction. It will not go from M to the VN side, and it is not going to follow that direction. We need to keep the original arrow's direction. Okay, so we should not be going other way around. So this v-test is going to be multiplied by k. It's going to be reaching here as our old x of f. Now it will be subtracted from 0 in order to reach here, then multiplied by a1, and then we are reaching to vn. Now our loop gain is finding this ratio of vn over v-test. Then we are just following exactly what you did, what we said. So our k multiplied with v-test, subtracted from 0, multiplied by a1, then all of this is equal to vn. You do small rearrangement, and then you get vn over v-test, it's equal to minus k times a1. Okay? So this is what we are calling the loop gain. Now I am showing another example over here with a real circuit. Now this is an op-amp. First I have Hamza has a question.
Yes, ma'am. Just wanted to ask, how is this different from the loop gain that we found out in the previous example? The standard gain that we found out was A naught over 1 plus K over A naught.
Yeah, this is a different. I mean, so now we have three names of gains. We have the open loop gain, we have the closed loop gain, and we have the loop gain. So they are three different things. Let me just one more time say them. So the open loop gain is just A1 alone, assuming that you don't have this down path. Okay. The closed loop, the entire going from Y till X over X with everything included. This is the one that's going to be reduced. And the loop gain is that when you will make your input is shorted, and you will break the loop to see how much this loop is giving you without the input. The input is 0. Okay, this is called the loop gain. So we have three types of gains, and you should know the difference between them.
Okay, thank you, ma'am.
Okay, welcome. Okay, let me go back to the example. I did this. Okay. So basically here we have an op-amp. We will come later to the lectures of the op-amp. We cannot skip this topic because it's also a very, very important topic, but I will cover it later. But assume it's just an amplifier. Assume that inside this box is our differential amplifier, okay? For the time being. Now we have our input X is going into the positive side of our amplifier. And then the output Y, we have a resistor R1 and then a resistor R2. And from this middle point, we are taking it and multiplying it with any K factor. We'll see later what can be K. And then this is forming X of F. So now we want to find the loop gain of this circuit. So again, in order to find the loop gain, we need to do two things. First, we need to make the input short, means connecting it to ground. And second, we need to break this loop at any point you want. You may break it. It's better to always break it. The best location for breaking is where you are taking back into the feedback. Okay, where is the connection between the output and the feedback point? And that particular point, I think, is the best location for breaking the loop. Okay, so assuming now we have break it there, and we're calling this point as N and the other point as I, and we have also shorted the input. Okay, so now we want to find our loop gain, which is basically N over I. This is N and this is I. So we need to find the ratio between them. Again, we need to move in this direction. Okay, following the arrows direction. So the input is going here and the output is going here. We need to follow the arrows direction. So now I is going to be multiplied by K, and this is our X of F. This will be subtracted from 0 because 0 is going on the positive side and this is the negative. So 0 minus K times I, and this is equal to Y. Now, how to reach to N and Y? I mean, how I should get N from Y? You can see that it's a simple voltage divider. Okay, so we have N is basically equal to R2 over R1 plus R2. This is how N is related to Y. And then we just do a simple simplification of all what we have wrote here. You will find all the steps, they are here. So this is N equal Y multiplied with R2 over R1 plus R2 with a voltage divider. And then we substitute back in our original equation, and we get N over I equals minus K times A1 times R2 over R1 plus R2. This is our loop gain. Loop gain. Okay, any question on this? Yes, Ali. Ali, please go ahead.
Yes, ma'am.
Yes.
Ma'am,
Yes.
could you explain what is N?
N is
The
any variable name. You can change the name anything you want.
Are we taking the gain across R1 or
R2? Sorry?
The gain is taking effect of both resistors or just one?
No, I have to consider both of them, but I want to know, like, I reached until point Y. Okay, now how I should go to N, because in order to find the loop gain, I want to find the ratio between those 2 points that I break the loop across them. So one I just named it name N, and the other named I. You can change the name any way you want. Now how I took, just to make sure that everybody got it, N and Y is that I need this variable N. How should I get it? I will just find a voltage division that is here. So in the entire, this has a voltage of Y, how much this N will be. So it's a voltage divider. Anybody else having question here? Let me see. Hamza, Athar.
Yes, ma'am.
Please go ahead, yes.
I just needed to confirm one more thing.
Yes.
When we break the loop and find the gain, we actually have to find it between the points we've broken, or between the output sensing point and where we've broken.
Yeah, between the 2 points that you have broken here. So it will be the one on the output side, and this is, we are assuming, the input side. So it will be N over I. This is our loop gain, because like going all over our loop from where we started until we reached here. So this is the loop gain.
Thank you.
Okay. Anybody else having question here? Seems to be no. Confirm. Okay, nobody having question. Okay, so this is the loop gain. Now, just one last example on it that I did is basically, now we have replaced the K with this common source stage. Can you see? So now the input I, or let's assume that there was no breaking. So the output was going from Y and then onto the gate of this transistor, and then we are taking it from the drain of transistor and feeding back onto this point here. So now what happened, if I break the loop here, again at the input of the feedback side, so this is, I'm calling it I, and we are calling it here N, and this is open now, which is we're putting lines on it, dashed, so it's open. Okay, so now the steps will be exactly similar to what we did before. We need to find the ratio of N over I. Now, how I became X of F? It's going to be multiplied by K, but what is our K here? It's basically going from an input of a common source till the output, means that you are multiplying with the gain of that common source amplifier. So what is the gain of a common source amplifier? It's minus GM times RD in parallel with the R out. Again, either you took care of the R out or not, it's not the big deal. The main thing is that you need to know that this is a common source amplifier. Now, if I replace it with another, I add another stage of a common source here, this means my K is going to be GMR out all square, means 2 times I'm having a common source amplifier. Okay, any question on this? Isha, please, Isha, go ahead. Please unmute your mic so we can hear you.
Yes, so ma'am, what my question here is that when we're observing the amplifier, the
Yes.
op-amp, isn't it that it has a configuration similar to an inverting amplifier?
Yeah, here, if our input is going on the positive side, so it's not an inverting amplifier. You are talking about whom? The K1, the common source, or you're talking about the A?
I'm basically asking about the original amplifier, which has an A1 labeled over it.
Yes.
So if I look at the configuration of the resistors and everything, can I not just simply relate it to an inverting amplifier that simply has a gain of minus RF over R1, where I can identify these resistances as being RF or R1?
Yeah, the first thing, this is not an inverting amplifier because your input is going onto the positive side here, but now we are grounding it for the sake of
I thought this
finding the loop
was
gain.
negative, the one which is on the lower side. The positive side is grounded, right?
Yeah, this is negative, this is positive, and this is negative.
Right. So the positive one is grounded, while the negative one is connected to the rest of the network, right?
Yeah, I'm talking about the entire one, assuming that the input is there. But if you are talking about that, just assuming the input is coming from here, yes, you're correct. Then it's inverting for this side that is here. Now, because I have not discussed with you how to find for an inverting and non-inverting amplifier, I didn't cover chapter 8, so I cannot assume that you have this knowledge.
Oh, okay.
Okay, therefore, like I'm trying to, we will come back when we talk about chapter 8, we will discuss the inverting and non-inverting and how to find their gains. But now I cannot assume that you know something that I didn't teach you. Okay, but
thank you, ma'am.
Is it clear?
Yes, it's clear.
Okay, thank you. Let's see who else is want to ask his question. Okay, Ali, do you have a question? Yeah.
Is point I and N connected with each other or not in this case scenario?
And I mean, in the original amplifier, they are, but now when we want to find the loop gain, we will break the loop. So they are not connected.
Okay, thank you.
Okay. Anybody else having question? Then by this, I am done from talking about the loop gain. I want to talk something more. Okay, let me just remember what we did over here. Yeah, one more point about the loop gain is that we always want this loop gain to be very much large. Okay, so we want it to be K times A1. Yeah, by the way, just forgot to say this important point. Sorry for missing it. Yeah, that. Here, most cases, this KA1 is going to be our loop gain in many cases. So it is basically, we want it to be very large. And if we assume that it's very large, here we go back to our closed loop transfer function, then we can assume that this part 1 plus k times A1 is, since k times A1 is much larger than 1, then adding this one can be neglected, this plus 1. If you do so, you will get A1 divided by k times A1, which then you can cancel A1 with A1 and you get a closed loop gain of equal 1 over k. So our closed loop gain can be approximated. If k times A1 is very large, then you can approximate y over x, the closed loop gain, as a 1 over k. And this is a very, and this is a very important point here, is that basically you make, by closing the loop and having a very large open loop gain, which is A1, it allows you to have a very controlled gain when you close the loop, and it's equal to 1 over K1. So now you can see that our closed loop closed loop gain does not depend on the open loop parameters. Means it's not depending on GM, it's not depending on an R out, it's not depending on all these ones. It's not depending on the internal transistor relation. It depends on the feedback configuration that we have. And that we will also see on chapter 8. And this basically has many applications. It allows us to create a very controlled gain values. So we are not affecting, we are not being affected by the manufacturing process and all that. So this is a very important note to note, that if you have a very large open loop gain, your closed loop gain can be formed and can be dependent only on the feedback configuration and not on the forward path. This allows you to have more controlled gain formation. Okay, so this is we need to keep in mind as well, and we will see how. I try to link it back to you here when we cover on chapter 8, that these things are really correct. Okay. Okay, there is one more example, is similar. This example is exactly similar that to the one which we have discussed here before, only that we don't have any amplifier that's here. We don't have any K, so we assume K as 1. And then the rest of the steps for calculating the open loop, the loop gain will be same. So here we don't have any K, K equal to 1. Okay, now the last topic that I discussed in the first lecture is basically to see how the input and output impedances, they are going to be affected by closing the loop. What's going to happen to them? Okay, now we can see this is an example that we are discussed in the lecture. So basically, if we assume that it's an open loop, there is no feedback, this path here from the input to the output is formed through a common gate amplifier. Okay, so then our A1 or A0 here is a GM RD, which is the gain of a common gate amplifier. Now we have a feedback here formed through R1 and R2. And then we are feeding it back here into the gate of the amplifier. Now feeding it back onto this gate is helping us to form the subtraction function that we saw. So it's in order to do this task that is here. We need to form this subtraction. How this is going to happen here? There is only one input side on this one. That's why we are filling on the other side and getting the subtraction by subtracting VG minus VS and getting a VGS. So we are subtracting X of F minus our input X. And basically this VGS is going to create our current, that is ID following here. So ID is equal to GM multiplied with VGS. And then, so we find the closed loop gain by just replacing the values that we know here. Again, here we are assuming an infinite bandwidth because we're not showing any capacitor in the circuit. Otherwise, if there is a capacitor, you need to take care of it. Okay, so now our open loop gain is GMRD, our K feedback formed by, again, the R2 divided by R1 plus R2, the resistor or the voltage divider. So this is our K value, and this is our A0. So we got the closed loop gain. Okay. Now the last thing which is important here is we want to see what happens to the input and the output impedance. Since it's a common gate, the input is impedance going to be 1 over GM because we are looking from the source side to the amplifier, so it's 1 over GM, while the output is impedance RD. Again, in the common gate, we always in this book assume that lambda equals to 0 in order to simplify our calculation. That's why we're not considering R out here. Okay. So now, in order to find the input, the new input in case of the closed loop configuration, 1 minute. Yeah, we need to apply a test source that is V test and have a current output I test and find the ratio between VT over IT. Now, this is not so straightforward. First, we know that IT is the same, the current that is here, so it's equal to the ID of the transistor and it's equal to GM multiplied with VGS. Now, in this example, we are also assuming that R1 plus R are much greater than RD. Okay, so since they are much greater than RD, they're going to be a much lower current that's going through this path compared to RD. So we may assume that all the current is going through RD because current always likes the low impedance path. So the current, assuming that the current all IT will go up and not going into the R1 and R2. So now we will replace, this is GM, we are just replace. VGS is basically VG minus VS. VS is the test voltage, while VG is the voltage that is here, is basically the V out. So this part is V out multiplied with the voltage division R2 over R1 plus, it's not shown. Yeah, multiplied with R2 over R1 plus R2 minus VT. This VT we said it's the source voltage that's coming on the source of the amplifier. Okay, now how V out equals to IT multiplied with RD? Now, if you look at the small signal model, you assume again that the VDD is going to be converted to a ground. So the V out is equal, all the current that's going here is IT multiplied with this RD transistor. So this is the V out multiplied with this voltage divider in order to get this VG that is here, and this is VS. Okay, so VG is equal to V out with multiplied with the voltage divider here, and the VS is exactly equal to VT. So now, after you simplify this equation, you get VT over IT equals to 1 over GM multiplied with 1 plus this voltage division multiplied with a GMRD. So what do we understand from here? This is the main point, that the new closed loop input impedance equals to the open loop open loop input impedance, which is 1 over GM, multiplied by 1 plus, this is our K here, and this is our open loop again. Again, this magical factor is coming here. So our input impedance has been increased compared to the open loop gain by a factor of 1 plus K times A1. Okay. Now, in the last thing, which is basically about the open loop, the output impedance, again, we will assume the input side is shorted. We'll apply the V test from this side here, and then you will find now VGS is just VG, because VS is equals to 0, and VG is this nodal voltage is VT. So it's a VT multiplied with this voltage division, and ID equal to GM multiplied with a VGS. Again, we replace the VGS with its value, assuming that same assumption, R1 plus R2 is much greater than RD. Then you will assume that your IT, the current that is coming from here, is equal to the ID of transistor plus the current that goes up here in the resistor. There is no one that is going into R1 plus R2, assuming no current again is coming here. So now we replace ID with a GM times VGS. This is ID. And the the I that goes into the resistor is basically the voltage over this resistor, which is VT divided by RD. And then we will do this again, rearrangement once more. So we will get our output impedance equals RD divided by 1 plus R2 over R1 plus R2 times GMRD, which is our open loop gain. The same, we come to the same conclusion, that the closed loop impedance, output impedance equal to the open loop impedance divided by 1 plus, again, K times A1. So here, our input impedance has been increased by a factor of 1 plus K times A0, while our our output impedance has been reduced by a factor of 1 plus K times A1. So we have like a one impedance has been increased and one has been reduced, and we will see that both, in this case, both are advantages. They are not bad things. Yes, Ali, please go ahead.
Ma'am, two questions.
Yes.
Number one, that why is it that we replace, we add an NMOS in the circuit at that certain point, like where there's an operational amplifier initially, when we are sorting out the circuit, you place an NMOS over there. What's the reason for that?
Yeah, here it just came by luck. It's not always that we, for a simplicity. Otherwise, I have to show you a big circuit of a differential amplifier inside of that one. But I mean,
Okay, so
let's say every case of you see an op-amp or that symbol, it always have inside it a differential amplifier. Just for the simplicity of understanding, I'm explaining it to you through a single transistor.
Also, ma'am, could you explain the working of how the output impedance is being decreased?
Yeah, it's our original output impedance, the open loop case, as we just showed them earlier. It's just our RD. It was an open loop. Now it become an RD divided by 1 plus this voltage division component, that is R2 over R1 plus R2, multiplied with the GMRD. This is K and this is A. So now it's the original output impedance divided by 1 plus K times A1.
Okay, ma'am. Thank you.
Thank you. Anybody else have any question? For this is what we have covered in the entire lecture 1. The rest about, I will be talking about it next time. So if you have a question about this one, that what I just discussed, you can ask me now. It's all clear? I don't see anybody raising hand. Any question? Okay, I have Abdullah. You have a question.
Ma'am. Ma'am, I wanted to ask, can you somehow improve the quality of the picture, the Droid Cam client you are using?
Yeah, I'll try to, basically I'm limited with the resources that I have, and the markets, they are all closed. I will look around if there is any market that sells these things. If you are aware of one that sell any camera or some sort of thing that can be useful for our recording, I'll be more than happy to do that.
Okay, ma'am.
Okay, I'll also, when I am uploading them for you, you can, one more time, if you, any part that you still find, I'll be also record this, all our discussion is hopefully recorded. So we can share it as well. So you can go back to that part and look at it again. If it's still missing, like you're still not understanding it, we can again discuss it.
Ma'am, apart from that, when would we be getting our mid results back?
Yeah, we are grading them. It will be hopefully by tomorrow, they will be ready. So then I'll upload them, and I'll upload some pending grades on the assignment. I'll try to do that. It was, recording the lecture is not an easy task, as you would imagine. So that it was really taking much time.
Okay, ma'am. Thank you.
Thank you. I was not reading the chat because I was focusing on what's going on in the talk, and if somebody has a question, so I'll read your chats later. And anybody else having question, or we should stop here? Okay, seems to be no more question. Then we will meet inshallah on Wednesday, and we can, you will also, I'll have uploaded the next lecture sheets as well. So they will be with you when I am talking next time. So it will be inshallah easier. Okay? Okay, then I think we're done here. I'll stop sharing my screen. And thank you so much. Abdullah, you still have something to say?
No, ma'am. Sorry, I didn't lower my hand.
Okay, no problem. Okay, thank you so much for everyone. Thank you. Allah Hafiz.